Yo, what's up, everybody? Welcome back. Today we are looking way too closely at random number generation. So the context here is I wanted to, um, I wanted to track what food I was eating, and as part of that, it became like kind of interesting to say it would be like what's in my fridge so that I could like automatically generate grocery lists based off of like if I'm running low on milk, and then I don't have to think about it. That'd be kind of cool, which means that like I need to like keep inventory of stuff in my fridge. So maybe like scanning barcodes on my phone as I put stuff in the fridge would be kind of good, because barcodes would give me like a unique identifier of like, oh, this is a container of milk and that milk is 2 liters. And then when I like make coffee later and I say I use 20 milliliters of milk, I do that like 1,000 times, 100 times, whatever, then I'm out of milk. Crazy, right? So then we got into this like track of trying to write a barcode scanner by hand that like takes photo like from photos on my phone. It turns out that this problem is like weirdly not trivial. You would think it's pretty straightforward, but there's a lot of scenarios that like make this hard, right? Look at this, like that's weird. That's kind of interesting, right? Crinkly bag. You got like motion blur. You got like barcodes that have like weird speckle patterns all over them. You got like low light sensor noise. All of this stuff is not like me trying hard to make degenerate cases. This is literally just like photos I took in my house, right? Mostly. These ones are from the store because I saw a bubbly barcode at the store. I'm like, ooh. So we're like, let's train a neural network to do these things. And how do we want to structure the problem for the neural network? Not really super sure right now. I suspect like the easiest problem for the neural network to solve is tell me if I'm inside a stripe or not, right? So basically finding some way to filter out all of the shit that I don't care about. But to do that, you need like data of barcodes to show the neural network to train it. Hey, this is inside the black bars, this is not. And to do that, like you need data, right? And nobody online has gone through and like taken photos of barcode and like colored in with a pencil all of the pieces that match, right? And if they had some algorithm that would automatically do that, that solves our problem for us, right? So this doesn't exist, right? So we want to make it ourselves, which means that we need to generate barcodes and like fuck them up, right? And one of the you know, kind of the core of fucking stuff up is going to be random numbers. We want to do this on GPU because it's faster and more fun, and we're kind of like in the mindset of GPU programming right now. So, you know, to do something like this, what we would need to do is we need to generate a barcode. We would then need to generate for each pixel in the image, we would go, hey, give me a random number. And I want that random number to fit a Gaussian distribution because that's the distribution of like noise on a real sensor in real life, and offset the pixel value by something in that distribution. And that's like just a weirdly not trivial problem. We need a source of randomness on the GPU that is like heavily parallelizable. We need a way to convert whatever those random numbers are into the range of like 0 to 1, let's say, and then we need a way to convert like that uniform distribution into a Gaussian distribution, because we don't want uniform distribution. So there's all sorts of stuff to look at there, and so that's the plan for today, is to implement all of that. So let's jump in. Step one, parallel random number generation. There is this paper. So if you look up like TensorFlow RAND algorithm. This is kind of where I started. You just kind of like, I'm just looking around for what other people are using. But these guys talk about this thing, Phylox and 3Fry. And it looks like, as far as I can tell, looking around the internet, are there not any barcode reading libraries? Sir, you don't get it. It's not actually about the barcodes. But there probably are. We don't look at libraries around here. That's crazy talk. we like pain, masochism. That's us. But yeah, okay. So basically, everything that I've found online while researching this comes from this same paper. Parallel random numbers as easy as 1, 2, 3. And they kind of, you know, I've read this like several times. It took me a while to like kind of get it. But basically, they kind of start with the point of normal random number generators. They do this thing where they have some like number, right? And you like apply a bunch of like stuff to that number to like transmute it in some way. And every time you pull another number out of it, you like transmute that number some more. You go over, number goes bloop, 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 new number, and like you get a stream of random numbers out of it that way. Right? This is different than like if you were to pull random numbers from like the kernel, well, kind of. Okay, so like when you boot your computer, you like move your mouse, there's like some like electrical noise on your motherboard, like the network card might be getting some stuff from Ethernet. There's all sorts of like sources of like randomness, right? And one thing that you could do if you want random numbers is you could just like look at those numbers, right? You could be like, okay, I've like looked at all these things and like there's some randomness there. But that is not like an infinite source of randomness, right? You might deplete the pool of entropy very, very easily, right? And so what they do is they like feed these things into like random number generators. And so that's what I'm talking about here is you seed this thing with some like initial real randomness, and then you just transmute that thing in a way that's hopefully not like predictable, right? So you use like cryptographic techniques to try to like make it so that you, like the next number is like a number that you can't predict. Hand wavy. So the observation in this paper is that there's kind of like two pieces of this number generation. One is like state transmutation, right? So like going through and changing the thing that you're holding and like fucking it up some more so that you have like a new thing that you're holding for next time. And then there's also like looking at that thing and observing it, which is a second step. And so this paper says, hey, like your state, we can like readjust this problem such that your transmutation of state is just like a counter. You just keep going up by 1, 2, 3, 4, 5. No more of this like crazy like sequential XOR multiply bit shift bullshit. Just like count, and then we'll move all of the XOR multiply bullshit into like the observing state, and you can spread that out over all of the cores of your GPU. They also make the observation that this is very, very, very similar to counter mode block ciphers. So these guys are like when you do encryption, how the encryption algorithm works, hand wavy, there's like this building block of a thing that can like take some text and like change it in some like, can I fucking open image by itself? Like take some text and, you know, do something that like transforms that text into some ciphertext. And one of the modes of these things is in counter mode. So you can like start with some like some cipher, and every time you like increment the counter, and then shove that into this cipher, you get like another like a unique set of zeros and ones that you can XOR with your input to make your output. So like this fucking exists. Like AES is doing this shit. Like what was the other algorithm they talk about? AES and like 3 something. Where is it? AES and 3 Fry. They're like, both of these guys are like good. Now they're like, now the reason that people don't actually use these for PRNGs, despite the fact that they would be very good at them, is because they're fucking slow, right? So they kind of like strip away some of the cryptographic properties of some of these algorithms to try to get them to be more efficient. And they basically say, hey, these guys are doing a bunch of stuff to kind of like obscure the like key, right? So when you're doing like cryptography, you typically have like some data, a key, and that key allows you to do the transformation in a way that's like reversible, right? You can use that same key to undo the transformation later. They are kind of saying like, as part of the process of like iterating this thing and shoving data through that key, you're trying to do some stuff so that it's not like trivially easy to like get the key out of the data, right? Hand wavy. And so like we can just not fucking do that stuff. And then they also observe that like part of the things that these cryptographic algorithms do is they might like apply some simple transformation, but do that like many times, and that becomes a complex operation. hand wavy. I don't really understand this paper very well, but like that's like the understanding I have after skimming this like several times. And so they have like some examples of algorithms that like one is based off AES, one is based off of three fish. AES and three fish mapped to ARS and three fry in their world. Where they've basically kind of like stripped down the guarantees of like key security. They make one more observation, which is that if you like really, really don't give a fuck about security, you can actually go farther and you can basically get through like some of the, or when I said like you do this like simple operation a bunch of times in a row to get like a more complex operation, they're like that simple operation can be as simple as multiplying two numbers. So you just multiply two integers, you take the high half and the low half because they're like you're doing like 64 bits of multiplication for if you multiply two 32-bit numbers, you might get like a 64-bit number out. So they're like, we take both of those numbers, and if we chain this multiplication a bunch of times, combining with some of the strategies of like fucking the number up from the cryptographic stuff, basically like something like this where you have like some inputs and you just kind of like shuffle them around. With the combination of those two things, we can get like a thing that's very fast and like uniformly distributed in a way that like they keep talking about this like crush resistant thing, which is like, I don't know, I didn't read that part. Like some test that's like, are my numbers random? They're like, yep, they're still random. Yeah. So that's kind of like what this thing is. They have an implementation of this random 1, 2, 3. And when I looked at this yesterday, it was like unreadable, but we can get there. So we can look at their implementation that goes with their paper. And in here, they have an implementation of phylox.h. This is the be all end all, the fast parallel computation thing. And this is probably what we're going to implement. And if you just like scroll this, you start to see some like pretty wacky shit. Like, R123 array 4x pound w underscore phylox 4x pound w pound round, like that, which calls mul hilo pi pound w with phylox m4x pound w pound underscore 0. It's like, what are we talking about, man? What are we talking about? Because oh, that's just doing C++ templates in C. Yeah, it's just like hard to, if I'm trying to figure out like what are the multiplications they're doing, it's actually like kind of not trivial. But we can just pre-process this file and call that the thing that we're looking at. Can we call this phylox pp.c or something? And then can we like Clang format that thing and take a look at it? Yes. Okay. This is gonna be like, can we, grab, like, we need to remove all of the preprocessor tags. So can we do like grep, filter out things that start with a pound? Probably like this. Maybe like this. Yeah, better. And then we can Clang format that. Okay. So this has a bunch of like type tests and shit, but the key of stuff that we're looking at here is this like phylox, wx, I think it's like nxwr, where n is the number of numbers that you're trying to output, and this number is like the width of those things. So if we look at like their paper, or the fuck that was, they kind of have like, hey, we implemented like 2 64-bit, 4 32-bit, and we ran them like some number of times each. But like hand wavy, we're probably looking for 2 by 32 if it exists would be probably good enough. 4 by 32 is like fine. Let's see what they have. They have 264, 464, 432, 232. Like, I suspect that 232 is like good enough. That's not even on their list here, huh? Yeah, so maybe 2x32 is not good enough, and that's why they don't like it. But are you planning on validating your implementation, drawing distribution or something? Yeah, something like that. Something like that. And you know, the pre-processed version of this is actually not that bad. So you have like your counter, right? So this is oopsies. This is like just a number between 1 and 2 to the 32 times 2, I guess. Sorry, 2 to the 64 is what this is. Then they have a key here, and this is like, you know, if you think about this in the context of block ciphers, this is like the thing you're encrypting with, but in this context, it's kind of like the random seed. So this is going to be the same across all numbers in your distribution, but like if you want like different, you want to like run it again, you can seed a different number and like you'll get like a different output, right? So key is basically your seed, counter is where you are in the stream of numbers, and what is R here? The number of iterations that you want to do on this thing. And so they kind of say like, hey, one iteration of this is literally just like multiply this magic number by 1/2 of your number. Then do some XORs to fuck that shit up, and then return that. Easy, right? Then you just do that many times, and then you also like do some adjustment to the seed value for each iteration of this thing. So they just add another number to this. And then they just do that a bunch of times and return the output. Easy. Easy. I had to do so much fucking reading to basically understand multiply XOR add. But we got there. We got there. So let's try implementing like 2x32, maybe. I guess we could look at 4x32. It's gonna be the same thing, right? But just with like different magic numbers probably, and then also like different numbers of multiplications. But yeah, let's start with the 2x32, and then we can kind of see if like the distribution is like fine. It probably will be. So I don't know. In here, probably if we have like a math executor, and I guess this is probably where this belongs. So the math executor will have like a random function where we feed in, I guess like a number of dimensions or size of this thing that we want to generate random numbers for, and it will generate that many. Hand wavy. Math executor. So, and I guess probably he's going to feed in the key and the start count as well, probably. Right? So we're going to be like random. He's going to take in some allocator to put the output on. True. We're going to have maybe dims. And he's going to return a tensor. Okay. And we also want the seed as a U64. And the start count as a U64 as well. Probably something like this. So this guy's going to have to launch some program that runs on the GPU. They call them kernels. So we're going to have to like make one. So let's make a rand program. And we need to like extract that guy. We need to like compile him and for our GPU that we're running on at this time of running the program. So rand program comes from the rand program content. And then we pull out the kernel from this guy. So this is going to be like rand program and then like get the kernel, the function that we can run of rand. Phylox maybe? Maybe rand. This is fine. Do we care a lot about performance? Some PCG variant might be good and fast. Link to Wikipedia has implementation of the suggested variant, 7 options. What does PCG mean? Permutated congruent generator. I didn't get here. So does this not mean that we have like sequential state? congruential. Maybe not. Is this just like a thing that sits on top? Ah, yeah. So you apply some like rotations and XORs and all this shit to like make the number more random. Is that what this is? It's a hash. State based. Interesting. But you could instead of using, yeah, so I think that we don't like, so in order to make this work, I think that you would need like one state per pixel or something, which is kind of what we're trying to avoid. I think. Right? So by doing it this way, the only state that we have to hold is like what number we're on for the whole set of all numbers. For the whole, sorry, for like, we can generate as many random numbers as we want out of one number versus having to like store state for every output that we're trying to make, if that makes sense. If that makes sense. So I think that's kind of why like something like this wouldn't work, is because we would need a state for every single output. I think. But I might not understand, because I might be fucking, out to lunch. Okay, so this guy, we shove him over here. We say we have a rand kernel now, and we can use this thing somewhere. We just have to figure it out. Where? RxS MXS is the 32 to 32-bit variant I suggest in that doc. No, oh, I forgot to read your doc. Yeah. Oh, right. So you are talking about. I see. So what is the like pro of doing this? Maybe I'm not understanding. Like what is this doing that like Filox is not? No big state. But isn't like, don't you still need one state per stream? Where each stream is like each pixel? Like if I'm trying to generate like 1,000 at once, isn't that a problem with this? I suggested in that doc, input state can be compute invocation ID for the first run, and the rest just iterate on the previous step. Okay, yeah. I understood. Yeah, I think that I didn't want to do it that way because I didn't want to like hold a texture for all of the previous state. Like it means that you're kind of limited to like generation of n random numbers at a time, where n is like the amount of GPU memory you're willing to eat at that point. Like, sorry. You can only hold as many states as you're willing to hold, I guess. Which is probably enough, because you can just do it more in a row, but I do want to keep going down this road for now. I'm already committed in my brain. Because this way you only need like literally one number. Okay, understood. I'm just gonna keep going. Rand CL. What does this guy look like? What do these other guys look like? Kernel, it's like a normal C function. So this guy is gonna take in like an output buffer. And then a number of outputs. Because, for these OpenCL like GPU kernel executions, you need to issue a multiple of like however many items you can fit in a work group, they call them. And so we might have to like dispatch too many, right? So we put the number here to say bail out in that case. So if, we say like we have some global ID. So this is like, I am running for one of like many pixels or many random numbers. Which one am I? If this is too big, return. Okay, in here we probably also need the state, the initial counter, right? And then we say we take like global ID plus initial counter, and this is the counter value. This uint is probably the wrong type, right? I assume like OpenCL types, I assume that we have like a U64 that we can use, but I don't actually know. Unsigned long or ulong. So we probably want this. Okay. Which probably means this is probably better. Yeah, it's fine. 2 to 32 numbers is a lot. Okay. We also need the seed. Like this. And is that it? Then we just do the file lock shit. So output at global ID is equal to file locks initial counter and seed. Is the seed definitely 64 bits? I don't know. I'm not sure yet. Random 123. Where were we? It was like include random 123 file locks preprocessed. So if we are doing like file locks 2 by 32, their key type is 32 bits. And their counter is long. So their seed is actually a uint in this case. Yeah, you don't want to derail just spitballing to hear downsides of chat. You could keep a single uniform for push constant or whatever that you offset the invocation ID and increment that by width times height for graphics or group size for last dispatch for no reuse. So no reuse. Yeah, I guess if you're assuming, I see. So you have like one state number, and you're kind of having. So what I'm doing is I'm running in this example of like file locks, you're creating like one stream of random numbers, and each pixel is pulling from that same stream. You can think about it that way. What you're saying is you have like many streams of random numbers, and if you assume that just like permutating state results in like equally distributed random numbers, then you only really have to apply the state transition on one of them, or something like that, which I would be hesitant to do because I don't understand. If I'm understanding what you're saying correctly, but like, doesn't mean it's wrong. Okay, so is that really the only inputs they have? Counter and key and the number of rounds. We'll just hardcode that. So this returns a u long. I guess 2x32 is the same as 1x64, huh? But like, fuck it. Do they have 1x64? They do. Oh, that's array 1. They have 1 by 64 array, but they don't have file locks 1x64. So this is kind of the same thing. Okay. 2x32. So it's fine. We can do it their way. So we are taking in a u long counter and a u int key. From a GPU perspective, 2x32 is probably more sensible because GPU registers are typically 32 bits wide. I assume that like the compiler will turn these ulongs into 2x32s, and then I don't have to think about like generating a new struct. But yeah, I could see the argument. Like, is it possible that when I do like counter shift right by 32 to extract like the top n bits, like is it going to do something fucking stupid? It might, right? But we can hope it doesn't. We can hope it doesn't. So they have file locks 2x32 round, which is like one iteration of the algorithm. And then they have bump key. So this takes in a key and it puts a new key. And their bump key was really straightforward. It was just like add this number, right? return key plus. Why are they doing this? Is this the thing I have to worry about? Surely not, right? I don't remember C enough to know. Is this thing like an int by default and then they like are casting to uint because of bullshit? Or are they doing that because like sometimes the key is too long and it's like generic code? I would assume the second one. Okay, so this guy, they're doing mul high low 32, which basically just multiplies these two numbers as u-longs, takes the bottom half and the top half and outputs them somewhere. And they are using them independently in this step, so that makes sense. So I guess we take this number, u-long, like m, I guess, is what they called it in the paper, I think. They are multiplying this by the... I guess we get to pick if we are using the bottom bits or the top bits here. So we can say uint CTR low is CTR and CTR high is this shift left by 32. And then we can kind of implement this thing the same way. So they have mul high low here, which they're taking the uint 64 cast of both of these guys. So u long of CTR low times m. This should be going in round, to be honest. This should all be going in this. Okay. So then I guess this is like the mul out multiplied. Then they're taking the top half and putting them in high, the bottom half and putting in low. Okay. And then what are they doing with this stuff? They're doing the output is, it's like uint out. Oh, so here they're saying low is the second one. So that means that here they're using CTR high here. Just for consistency. We can do that. Then the output of this thing. I think there's a CLC primitive functions for manipulating the high and low bytes from along, by the way. I've assumed that the compiler will figure this out for me, so I'm not really too worried about it. But if it doesn't, then I guess we can get a little bit more clever. Okay, so the high bits here are multiplied high XOR the high bits of the key. Oh no, there are no high bits of the key. So this is just key. XOR'd with the low bits of the counter. And then out low is just the multiplied low. So then we can return u long out high shifted left by 32 or multiplied low. I think this is the same thing. I think, right? So they take this guy, they do double multiplication, like uint 64 multiplication of this thing. They take the top bits and they put them in the high output and they return the low output. So they have low high here. Multiplier, u long multiplication into multiplied with the high bits here. Yup. Then we take the high and low, extract them like this, and we do high XOR key, XOR counter low, and low. Yep, I think that's right. I think that's right. So now all we have to do is we take this thing and we run it. So in their paper, do they say like how many rounds that they want to do? They don't talk about the 2x32 case really in the paper, I don't think. What do they do? I guess. Oh, here they're saying. Do they talk about the 2x32 case? Maybe they just saying here that it's shit. They might just say that. Here we go. So for n equals 2, the file x2 times width heart performs r rounds of this stuff. All that remains is determine the multipliers. Blah, blah, blah. We search for multipliers that do blah, blah, blah. Yeah, I guess they just don't. The 2x32 stuff is stuff that they have in here and they just didn't want to do. I'm kind of down. If they don't like talk about like the suggested number of rounds, then like I don't really want to. Maybe we just do 4x32 instead. Maybe we do that instead. I'm down to pivot. So in 4x32, what are their types? Oh wait, hold on. Maybe it's in the code still. They have this 4x32 rounds. 2x32 rounds? Oh, wait, they do. They just say use 10. Wait, no, we're chilling. We're chilling. Maybe it's still shit. We don't know. But who cares? So here we do. They kind of manually loop unrolled, but I'm not going to really bother with that. So for each of these guys, they do a key is equal to filelox bump key. And then counter is give me a round of this thing. Okay. And then we do one iteration without bumping the key. Which makes sense because we have the initial key. We don't need to bump it. We only need to bump it in between runs, and then we return counter. Easy. Easy, easy, easy. And then we'll just say here, you know, filelox 2x32 round was 10 in filelox h. All right. Okay. So I think we're kind of chilling. I don't know what this error is here. He doesn't like that for some reason. Oh, maybe we have to annotate this with global. Yeah. All right. But otherwise, is that kind of it? I think so. So we should be able to go back into our Zig code now. And we should be able to like run this kernel. So we create some output buffer. I guess we need to do. How do we, when we have like. Yeah, okay. So we can do, outdims is like math tensor dims init with this thing here. We use that to do something to create a buffer. So we create a GPU buffer that lives on this lifetime and has this size. Okay. And then eventually return this like buffer like this. Dims is outdims like this. Okay, and then we just have to like execute the kernel. So it's like execute kernel. with the rand kernel. Okay. And n is, I guess, the size of the output. And then what else does this guy want? He wants like a list of arguments. So what does our rand CL look like? He has buff is ret. He's got ulong, which doesn't exist yet, but we'll have to make that. So this is seed. We got uint. Sorry, this is start count. My bad. We got the seed, and then we have n here. And so we just need to implement one of these for ulong, I assume. So this guy is looking for these args, and I guess we have... I guess we need to double check that CL set kernel arg can take U64s. Arg index... Okay, arg size specifies the size of an argument value. If the argument is a memory object, it must be equal to CLMem. For arguments declared with local qualifier, the size will be specified in bytes of the buffer. Okay, if the argument is of type sampler T, arg size must be equal to the size of CL sampler. For all arguments, everything else, it's the size of the argument type. Yeah, so it should be fine to be like, we are allowed ulongs like this. That should be allowed. I think, and then we can feed in ulongs like this, and hopefully everything just works. Hopefully. And I guess all that's left is to run this motherfucker. So can we just do something like if true return, then do some testing here. So math executor random numbers using our allocator. And can we generate, I don't know, random numbers of shape, maybe like just 1,000 one dimension? Seed, we will start at 0, and we'll just do 0, 0 here. Fuck it. Like numbers is this, and then can we just like dump them? Create file, numbers CSV, we can call them, so that they can open in LibreOffice. Out file, and then can we just like, I think we need to convert this to a CPU buffer. So numbers is to CPU. Who takes some like bullshit arguments for now because the API isn't fully flushed out, but that's fine. And now we can just say for each number, can we, if we just graph the numbers, is that going to be helpful? We might want to graph like a histogram of the numbers, but for now, let's just do this. Let's just see that we're getting like something reasonable. Like this. Okay, so that should do something interesting. He's mad because what? I actually don't know. TensorDim's in it here. Wrong allocator. Create buffer. Is he expecting like an allocator and read write? Buffer hint. Who else? No function named execute kernel. Is it like this? Yeah. Expected 3 arguments found 4. So true right now. Oh, he's expecting an allocator too? Whoa, hold on. I think it's like this, actually. Yeah, there we go. That's what I was looking for. Seed. Yeah, this should be a U32. True. Okay. Bad news bears. Those are all the same fucking number. Bad news bears. They all have the same seed? They shouldn't though, right? Or the seed, sorry, they all have the same seed, yes, but the counter should increment. Right? Because counter here is being incremented by the global ID. Pretty sure. Oh. Good point. No, you were right, because I was using the initial one instead of the one that we're supposed to use. So you were right. Okay, those are... it's pretty concerning that they all have trailing zeros, right? That seems like a bug. Does seem like a bug. My money is on like a left shift 32. Maybe. Uh, let's just see what happens if we do that. So good news is high and low here are numbers. And then I assume, yeah, it could be this. I would have thought that this is okay. Let's try this. Okay, so that's kind of working now. Now, does this numbers CSV look different? Interesting. Oh, it's because they're float. They have to be floats. Maybe. Right? Can we printf the counter here? Yeah. So our like math types here only support being floating point numbers. Can we do some like type punning to make this do what we want for now? This is like technically not legal, right? But I think that the compiler might let it. I think that if you use unions, GCC allows it, even though that's still technically not allowed. By C standard, if I remember correctly. So can we do float f uint u, and then we do like union fu val dot f equals this, and then we take this as a bitcast union. or sorry, U is like this, and we take the float point here, and then we can bit cast it back here when we output it. I think it's something like this. Printf, let's just make sure. I guess it's hard to tell if these are the same because they're like are executed in arbitrary chunks. But if we put out the global ID here, then we can correlate to what position it should be in the output. So like value 639 should be this, right? Yeah, so we see this guy here. So I think this is doing what we want. This is doing what we want. It's not good form, but you can perfectly well cast a float star to a U-long star and write integer bits to it, but it might not be a well-formed float. I thought that there were like aliasing rules or something that made that not allowed. I remember seeing like C-type punning. I remember this being like complicated. Like way more complicated than you'd think because of like aliasing rules. The C standards aliasing rules state that an object shall have its stored value accessed only by an LFI expression of a compatible type. Other values, the types float and int32 are not compatible, and therefore this code's behavior is undefined. Yeah. Oh, not good form equals undefined behavior IRC. Ah, I see. In C, you need to memcopy, and C below now bitcast. Yeah, and then I think that GCC accessing is an allowed form of type punning in C, providing that the read is not larger. I see, but I thought this was a GCC extension. Oh, but this is new. This is like new, maybe. I thought it was a GCC extension, but maybe that's old info. But anyways, I think this is allowed for now. Good enough. Good enough. So I guess what we want to do now is I guess we can try graphing these and see what happens. And I don't really know what we're expecting to see if we just graph what we see here. Probably nothing, right? Because like I guess like even like gap between numbers almost. But yeah, I don't think this will be very helpful. But maybe we can generate a histogram here easily. Yeah, I don't know if that really is telling me anything. What the fuck am I looking at? X-axis here is sample. Y is value. Yeah, this isn't really telling me a lot of anything. Can we like LibreOffice histogram? I don't want to like generate myself. Do they just have like a histogram function? So, hype. The fact that there are so many letters here makes me think it's not trivial. I ain't reading all that. I ain't reading all that. Buckets. We'll do like 1,024 buckets. Is a bunch of zeros. Then we go like 4 numbers and buckets something. How many, like we need to divide by some number to get it in the range 0 to 1024, right? So it's like shifted right by 22 probably, right? 2 to the 10 is 1024, right? 2 to the power of 10, and then, yeah, so 2 to the power of 32 minus 2 to the power of 10 is shift right by 12, I think. And what is he pissed about here? I don't know. Oh. N32U is a U32 bit cast of X of N. There we go. What the fuck is he talking about? Oh. Really? 22? My bad. Okay. Numbers? Is that what I'm looking at? So there's not enough samples here, right? We're seeing a lot at 0, a lot of 1, a lot of 2, a lot of 3, a lot of 4. So can we, can we just generate, like, way more numbers? Like 100,000? Oh, there are printfs in my kernel. That's funny. That's bound to cause problems. Or make it slow, but whatever. At least in C++, char and byte is specifically blessed. Yeah, that's. I think that the C standard also says that like anything that is an 8-bit type, so chars and unsigned chars are allowed to be cast from to make memcopy work. Yeah, there we go. That's not bad. That's not bad. So this is a plot of number of times we saw numbers between some range. And it looks like kind of like a flat, thick bad boy. So those are probably relatively random. GPU random numbers, baby. Let's fucking go. We could evaluate the randomness of it, but I don't care. I don't care right now. But the next step here is to turn them into floating point numbers. And this is not as trivial as you would think, right? So the naive thing to do is in our kernel, wherever the fuck we were, randcl, you could just do val u over 2 to the 32. I guess it's minus 1, whatever. 0x ff, right? Over the maximum integer value. However, this will give you, first of all, this number, I guess this number, I think this is probably not perfectly representable in floating point. Then this number is also probably not perfectly representable. And then also the step size of this is larger than like the step size of a floating point number, right? So all of those combined mean that this doesn't give you like, you're losing precision, which is probably fine. But not the fun answer. The fun answer is, can we construct a uniformly distributed float out of this 32-bit uint? Is this supposed to be 32-bit? Am I high? This is supposed to be u long, right? So we're also losing precision here. Oops. Out of the 64-bit int, that uses as much precision as we can, right? So let's jump back to floating point representation. Hello? Where's the picture? Here. So, floating points. They got a sign bit, they got an exponent, they got a fraction. Cool. So this is like a scientific notation number, 1 point something times 10 to the power of something else, except that you take the 10 and you turn it into a 2, right? So you have 1 point some shit times 2 to the power of some shit minus 127 so that they can encode both positive and negative numbers here, plus some sign, right? So what we want to do is we want to kind of fill in these numbers so that we are in the right floating point number. So we want to fill up this 23 bits with as much shit as we can. And so then what kind of comes next is like figuring out what exponent this number represents. So we thought about it. I will clarify, we did think about it, but we also cheated and we looked at Zig's implementation of this. So they kind of do the same thing. And we did get to the right answer independently, I think. And basically what they do is they manually construct a float out of a mantissa and exponent. The mantissa, they just take the lowest 23 bits, hype, and then they just pick whatever exponent makes sense to like map this to the right number, right? So if you have like, you have your number line 2 to the 64, 0, you want this to be 1, you basically just have to figure out like where on the number line am I and which power of 2 should I be, right? And so what they do in Zigland is they just count the number of leading zeros in the random number. And that seems to give us the right answer. Seems to. So let's think about this a little bit. So if we are at 2 to the 64 minus 1, technically, 1, this is like, and 0.9999999. 1 is not included in this range. This is going to be 0x f 0 leading zeros, right? Which would be like, what is the number that we want to put in here at this point? So we're gonna have a bunch of ones in here. So 1.11111111111 times 2 to the power of what? Probably like -1, right? Because you're gonna have something that's like you're gonna have something that's like 1.111111111, which is like almost 2 times 2 to the power of 0.5 is almost 1, right? Oh, sorry, times 2 to the power of -1, so this is 0.5. So almost 2 times 0.5 is almost 1. Hand wavy. So I think that makes sense. And then as you get farther, you want this negative number to increase. Yes. So if we are at, like, say we're like at half the range. So if we are at, int max over 2, this is going to be like 0b 0 1 1 1 1 1 1 1 1 1 1 1 1 1 all the way, which means that you do the same thing where your leading zeros are now 1 higher, so you decrement this exponent by 1 to get to like a quarter, times 2 is almost 0.5. Yeah, I think that makes sense, right? So you're saying like, if I'm like all ones up to some point, then I'm like almost 2 at whatever mantissa you pick. Okay, so now what happens? What happens if you are like towards 0, right? 0 b 0 0 0 0 0 0 0 0 0 0 0 1, right? Something like this. This is you're gonna get like 1.000001 times 2 to the power of negative big number. And I think that all works out. And then do they special case 0 in the standard library implementation of this, or do they just kind of like run that shit? If rand oh, so they have a special case for if all 41 bits are 0, generate additional random bits until a set bit is found. Or 126 bits have been generated. Interesting. So why do they do that? Why do they do that? Because RCR and STN was talking about subnormal numbers. So this form of a floating point number is only true unless we're at the smallest exponent. If we're at the smallest exponent, then this leading 1 doesn't exist. So they're probably trying to dodge that case. Maybe? What's the 41 coming from? That's confusing to me. The 41 is surprising. Is there something about 41 plus 23? Yes, 464. 41 plus 23 is 64. So they're saying, we want the fucking exponent to be set. And if... what's going on here? So here, I guess they're saying, hey, we fucking hit 126 zeros, just like fucking seed some shit in here. Because this thing should just be 0 now. This is probably like a magic number for 0, probably. Yeah, and so this 126 is what we were talking about before, how like the if it's you have no leading zeros, you want this to be -1. So 126 minus 127 is -1, which lines up with this formula here. So I think that's fine. And so if we really wanted to get crazy, we can just special case it instead of doing what they're doing. I think. So we just say if this is greater than 41, then we just set it to 0 or something. Or we like fill in the rest. How do we do this? So it just means that we don't raw dog the Mantissa, probably? Probably? I'm not sure. Maybe we just try to avoid subnormal numbers. But that means that we can't hit 0. That is interesting. That is interesting. So if we just try to say don't do subnormal numbers, how is 0 represented in here? With this is 127. So we could just round. Yeah, we could do that. We could just round it. I'm down to do that. Okay. So I think I understand. So it should be we have what? It's like float u long to float. And we say like, is there like a count leading zeros instruction in C? Is there like a built-in? Okay. Then it's like mantissa is val and the bottom 23 bits. So that's 8, 16, 24. So we want 23, so it's 7F here, I think. 8, 16, 17, 18, 19, 20, 21, 22, 23. Yeah. Okay. So now what do we do with the leading zeros? We say unit exponent here is 126 minus hold on. Minus LZ? Yeah. So we say you know, if val is 0xff dot dot dot, we want to be like 0.999999. This is 1.111111 binary times 2 to the power of -1, i.e. almost 2 times 0.5 equals almost 1. Yeah. Yeah. So is therefore if LZ is equal to 0, we want -1 exponent represented as 126 minus 127. Increasing for each leading zero. Okay, now we need to handle the like bullshit case. So, if LZ is greater than 41, was it greater than or greater than equal to in their version? Greater than or equal to, sure. Number, this puts us in subnormal numbers, which I don't want to think about. Round to smallest normal number or 0. Okay, so this is like, surely it's if val is greater than some number, we return 1.0001 plus some exponent. And if it's less than some number, we return 0, right? So that's easy. Then this is like, this must be like the smallest representable normal number, right? So it's like, sign bit 0, then followed by 0 exponent. No, 1 exponent. 127. So if we want like the smallest number we can represent here, it needs to be 0.000000001, which represents 1 minus 127, which is -126. Yeah. This is just return. So we want like exponent is 1, and then we want 1. I guess these can be all zeros. That's legal, I think. Is that legal? Surely. So it's literally just like so we need type punning here. So we have our float union or float uint union. So we have like fu ret u is exponent shifted left by 23, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah. We shifted left this by 23. That's the smallest thing we can represent. And return like this. Now we have to figure out what this like threshold is. And so this is, it's got to be like 2 to the power of 23 over 2, right? Something like this, because we have 23 bits of mantissa. Wait, is that right? Because 64 minus 41 is 23. Yeah, so this is just like this, I think. 64 bits minus 41 is 23 bits left in mantissa. So halfway is 22. This is crazy. We're losing 22 bits of entropy here. Fix me. This is a crazy amount of entropy to be losing. That's kind of crazy. That's pretty funny. But I think this will work. Okay, and then here, I guess this guy can live up here. And then ret u is equal to exponent shifted left by 23 plus or mantissa. And then here we can be like u long to float of this, I guess. This is u long val. Okay. I'd be curious to see what this does. So let's get these printfs out of the kernel. There's a good chance we fuck this up in some way, but we'll see. Okay, so how are we going to... I guess let's start by just writing them out. Just to see if they look sane. And we should just be able to log them as the floats that they are now. Okay, so good news is these are numbers between 0 and 1. Right? That's very good news. Now we want to maybe histogram them a little bit. So can we say 1024 buckets is maybe it's sure. So like for each number, if it's like we truncate probably into bucket size. So we just like times 1024 and then buckets at number times 24 int from float plus equals 1, I think. Then we write it to the buckets. Something like that. And then can we increase the number here again so we have like more samples? And then can we LibreOffice the numbers so we can graph it? Let's see if this looks the same. Looking pretty good. Looking pretty good. That looks like a uniform distribution of numbers. That's pretty sick. Pretty sick. I would say this is a success. Now, it's also good. We're not seeing like at 0. We're not seeing like a big jump, which is good. I was worried about that a little bit. We are still losing a lot of precision, but I think that's fine. We can kind of work with this for now. Okay. That's hype. What is the next piece here? The next piece is we want to turn this uniform distribution into a Gaussian distribution. Because we want to sample Gaussian noise for our image augmentations for our neural network training, right? So what does that look like? We looked into this a lot yesterday. So Gaussian distribution, also called the normal distribution. It looks like this, right? The like classic bell curve you see when in university your teachers wrote a shit exam, right? They show you this curve. They're like, boys, we want the curve at 70%. We'll just fit you all in this. You guys are normally distributed. You're normal. You're average. Okay, I want to close this, not fucking scroll up. And so the question is, how do I go from like a list of independent, like uniformly distributed normal numbers to like this, right? It means that you kind of want them like centered around 0. Well, thinking about it, you could imagine that like if you took the integral of this at any point, you would kind of know how many of all of the numbers you'd seen, right? So like at 0, you would get half of all of the numbers of this blue curve, right? So that is like a thing you can work with, right? They have the cumulative distribution function where this blue line is like how many of all of the numbers have we seen, right? And so this is going from like the x value of the distribution to like proportion of all numbers, but you can just like invert this, right? You would think. It turns out though that this function that they have involves the error function. Error function. And this thing is like some like natural log e shit. And it also turns out that like taking the inverse of this is not like a thing. An inverse of this for some value, you know, on this curve is it's not like trivial. It's like a thing that you can approximate, but you can't like get like a nice calculation of it easily. I think we were looking at hold on. It would have been in this to do. We had a link somewhere. This guy talks about it a little bit. Hello, I would like to go to this website. Enter, go. What is happening? Okay, cool. So this guy talks about it a little bit. He says we got some like pretty good approximations, but I don't like the idea of using an approximation to do this thing, right? So the other version of this thing is called the Box-Muller transform. And this is like exploiting something about polar coordinates. So if you imagine that you have two random numbers, like the angle of rotation in some unit circle and the distance that you have traveled from the center, where on this like line you are, you're going to end up with like numbers kind of like weighted towards the center, right? Because like if you evenly distribute here, you know, half the numbers are going to be less than halfway up the line. But then when the line is like also like rotating, that means that all of the numbers that are under half the line are in like the middle of the circle-ish, right? Now this doesn't give you like a normal distribution. This gives you, I like graphed this yesterday. It gives you something that looks like this. If you were to just like randomly select on this line and randomly select an angle, you get like some weird distribution that looks like this. Like the fucking line you draw when you're trying to be like, these sets of numbers are in this range, right? You get something that looks like this, which is very like non-linear. But then it turns out that like this thing follows, you know, something, there's like some E in here, right? There's like E's everywhere, you know, there's always an E. And so if you just like, instead of linearly going along this line, if you go along it in the to ln that thing and then square root it, you end up with something, right? And there's like probably some intuition here that you could follow that like the normal distribution has an E in it, right? So there's like some sort of like E and some square root in here. I don't know. I'm not going to go through, like, I don't really want to go through this math, but basically what they do is they say we sample in some like uniform angle, right? Great. And then also this like ln square root shit along distance along the thing. And if you take two random numbers, you get two normally distributed numbers out of that thing. Right, because you just have like the x and y component of that thing. It turns out that like both x and y in a circle are like equivalent. So you get like two normally distributed things, hype. So I guess, I don't really want to get to, maybe sometimes we do want to get to. So we could implement functions to do that. But for now, if we just want like one normally distributed thing, let's do that. So we'll just kind of take one of these guys. We'll consume two numbers from the PRNG. We will apply this formula to them, and then we should get some sort of normal distributed numbers, which would be hype. This thing is called Box-Muller, if I remember correctly. Okay. So can we do Gaussian here? And I guess we are going to kind of use the same parameters here, right? We're going to have some output, and we're literally just going to call... let's think about this for a second. Yeah, we can work with floats, fuck it. I don't care about losing a little bit of precision here, because it's too hard. My brain won't work correctly if we try to consider all the floating point precision issues that come with this. So we'll just call rand output, I guess we don't want to call rand because we don't want to write to that output member if we don't have to. So I guess we'll kind of just do this same thing here. Fuck it. We'll call this uniform val, and output global ID is equal to Gaussian val, right? And now we just have to kind of get that. So what is it? It's we actually have to sample this thing twice. So our global ID, I think we've multiplied by 2 here. And then we get two numbers, U1 and U2, and we just increment counter by 1 to get here. Right? Hype. Then we do, I don't know like what math functions are available to us here. I assume we have like squirt. Yeah. So it's like, do we have log? Is it just log is the natural logarithm or something? Compute natural logarithm, yeah. So log is natural logarithm. So we go square root of whatever the fuck, -2 times log u1 times cosine of 2 times, do we have like pi in here? We have cos pi, which is close. Which is the same, right? I think that gives us the same distribution, I think. Right? Because you have like a circle. The values from 0 to pi on x are the same as the numbers from pi to 2 pi, just like inverted. So I think this is fine, actually. I think this is good. And we'll say this is a Box-Muller transform, discarding, using only one value. Sure. Sure. Seems reasonable to me. Yeah, I'm not against it. Not against it. So here now we need to, our rand kernel, we are going to have a Gaussian kernel as well. And we store that thing here. And this guy is going to look very similar to the rand function, except he's going to be called rand Gaussian. All the inputs are the same. The buffer sizes are the same. It's literally just that we're calling Gaussian kernel. And I think everything else is like the fucking same. So you could put a fix me and be like a one-to-one copy of rand just with a different kernel. But for now, I'm not going to worry about that. And let's just kind of see what fucking happens. Okay, he's mad because I forgot a semicolon. If you're gonna be like that, you can be like that. Now he's mad that, did I spell this wrong? Yeah, I did. Gaussian val. Alright, try that. Now he's mad because call to cost pi is ambiguous. It is true because these are u longs, right? So we actually want float or u long to float on each of these. So true right now. And now he's mad because we didn't because this thing is right. So a Gaussian distribution here. First of all, what is like the range? What is like the values when we do this thing? With a standard normal distribution. So this is kind of interesting. Right, so these are going to be centered around 0 with, what is like the standard normal? So, blah, 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 blah. What is the fucking standard one? Is it u equals, like, mean 0, standard deviation something? U sigmoid squared is equal to 1. Okay. So, what are, like... So that means that our sigma is also 1. So standard deviation is 1, because 1 squared is 1, which means that we're looking for most of the numbers are going to fall between -3 and 3. That's going to be like the vast majority of them, because it's 3 standard deviations. I think it's 99% of numbers or something. If I remember correctly. So we want to kind of adjust this number so that we get that. So it's like, do we handle the sign bit here? In our u long to float? I don't think we do, right? Oh, we do, because this is going to return... Yeah, wait. Don't we need, like, the sign in here? Oh, no, because this is going floats 0 to 1. So is that what they want in Box-Muller? I assume so, right? I actually didn't check that. Yeah, it has to be, right? Because you're looking at radius and angle. So 0 to 1's there makes sense. So now we're going to have maybe negative numbers, which is great. And so here we're like, everything is going to be mostly between -3 and 3. So we want to distribute -3 to 3 into 0 to 1024, right? So we multiply this by 1024 over 6, then plus 512, right? Yeah. So bucket is n times 1024 over 6 plus 512. And then if bucket is less than 0 or bucket is greater than or equal to 1024, we discard. Maybe we log. Or we count them. Out count plus equals 1. Yeah. And then we'll just say like out count is equal to 0, and we'll log this at the end. This out of this out of bounds, and this should be on the order of like point something %, I think. So like, you know, like 3,000ths or something, I think is what we're expecting to see here. And if we don't, then we have to think about this more. But that's fine. What is this piece about? Or here, probably. And then we say buckets in from float bucket is plus equals 1. What's he pissed about? We didn't say how many elements. Nums. So 257 out of 100,000, which is about what we expected, right? I think. And can we LibreOffice look at the numbers? So we're hoping to see the bell curve here. That'd be kind of hype. That would be kind of hype. Oh, look at that shit, baby! Whoop, 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 whoop. That's a fucking Gaussian distribution, baby! That's fucking sick. That is sick. Okay, so the last piece here was we wanted to use this to, on GPU, generate an image that had like Gaussian noise on it, right? So if we want to like adjust the distribution of this thing, we just do like a multiply add to like offset the mean and distribution. So I think that's fine. So let's do some Gaussian noise shit. That's hype. That's fucking sick, dude. Okay, so let's do something like, I think we want like open CL kernel that will apply Gaussian noise to some input. Yeah. So can we do rand Gaussian? So can we do something that's like Gaussian noise, and we'll take in some input, some seed and start count for the random number generator, and output some tensor. So our output is literally just the same as the input. So clone input dims for the out dims. Our return is this thing, and we're gonna say like Gaussian adjust kernel, probably, I guess is a good name for this. And the buffer is ret. I guess we need an input as well, so we're gonna take our input buffer, output buffer, start count seed n. Sure. So Gaussian, what do we call this? Gaussian noise. Okay, I guess our we've been doing underscores everywhere else, which is fine. Okay, and then we compile, we keep track of the noise kernel as well. Hype, and then we go back to rand, and we have Gaussian noise. So this guy takes input, output, and he just calculates this thing. I guess we probably also want like mean and standard deviation, but for now, fuck it, right? We can handle that later. So can we maybe pull out a function here that's like Gaussian randval or something that takes in counter and seed? Kind of does. Yeah. It does this. Okay. So then we do this guy gets Gaussian randval like this with counter and seed. All of this goes away. I spelled Gaussian wrong again. And then here we kind of start with the same piece here. But instead of going to the output directly, we do output is equal to input. Yeah. Yeah. Sure. And then we probably we might want to clamp the output or something, right? So is there a clamp in here? Clamp min. We have f min and f max. There's really no clamp. Fuck me. F min this and 1 f max 0 and this. I guess probably doing it the other way makes this easier to parse. Yeah, okay. Sure. So he doesn't like this because we probably need to write F's here so that these things aren't doubles. Fucking C, dude. Okay, cool. Now, what we want to do is we want to create an input buffer of 0.5s or something. Can we, I guess, we might want to do something like, that's fine. It's fine, we'll just do this for now. So can we do create uninitialized tensor, like a I don't know, 1,000 by 1,000 tensor, right? So an image is 1,000 pixels tall by 1,000 pixels wide. And can we, I think that we have a way to fill this thing. Yeah, we have a fill buffer. So we can be set this thing to 0.5, right? Every value 0.5. I assume this is how this works. This should be exposed better, but this will work for now. I think it's like this. What are they asking for here? The size here is in bytes, actually. Okay, cool. So now we do Gaussian noise on this guy. So in image, like this. And we should see him get a little bit of specklies. So what we want to do now, I guess, is output this as a ppm. Because those are the easiest images to write out. So before we do anything, Can we actually just yoink in image out of this guy and try to draw a gray picture? PPM image format. I think this guy's really easy, right? So it's like, I think it's like this. I think it's like this. So let's open an output file of image ppm. You write out like it's P6 for the binary format. 1,000 by 1,000 is our image size, and then it's the max value is 255, and then so this is kind of like right all here. Then we go over each byte in our output. And I guess we do write out this thing 3 times. Which you can actually do this somehow. There's like a way to like address this. Is it like this? I can't remember. There's some way to index the inputs. Argument is in square brackets. Which is argument specifier. Oh, maybe when you are using a field name, you're required to enclose in square brackets instead of just numbers. So if we're using numbers, then we don't. It's just 0D, 0D, 0D. So we index the same number 3 times, and we multiply this by 255. And we do as, you know, U8 in from float of this guy, and he should be already in range, so he should be chilling. Should be. Okay, and then... Oh, this is supposed to be a binary format, though? So I guess we just do this, actually. Write this byte 3 times. Okay, I think that's right. Okay. What do we call this thing? XEG open, image ppm. So we're hoping to see a gray image type. And then if we set this thing to like black or white, hopefully that also, you know, is respected. Yeah, okay. So this is working. This is working. And so now we can just start fucking slapping our noise on here. So we run Gaussian noise and we say, could we look at the GPU output of this thing instead? And he's gonna get mad because we fucked up some code. Clone takes in just an allocator. Okay. Oh, right. So this is input clone. Dims clone like this. Gaussian adjust kernel doesn't exist, really? Gaussian noise kernel, I guess is what we called it. Okay. He's mad because floating point value out of bounds. That's not good. Because in our kernel, I thought that we clamped. I guess we clamped 0 to 1. Which is technically, we could get 256 in there, right? So, like, if we really wanted this thing to fit, it would have to be like a 255.0 to 256.0, right? I guess is like technically more the right answer. He still doesn't like that though, which is surprising. Because I don't... Oh, because we're adding... we take... Oh. Wait a second. We're not doing anything... Wait a second. output equals input plus, I'm a fucking high piece of shit. All right, let's try that. Let's try calling the function that I want to call. There we go, baby. Okay. So the question is, does this look like Gaussian noise? Let's go, baby! Let's fucking go! So obviously this is like extreme, right? We can try like reducing this thing. So like, you know, reduce the amount of distribution here. Right, so even lower, to be honest, like 20. You know, just like occasional speckle would be kind of interesting. Right, so, you know, this is like much closer to like the correct image. Even more, to be honest. Like, I want to see barely any change. Yeah, there we go. That looks pretty good. That looks pretty good. So you do see some sort of like noise on the image down here, but it's like pretty subtle. I think that's a win. I think that is almost a perfect success for the day. We're at 1 hour and 50 minutes, which is very close to the 2-hour mark. We've done Phylox RNG, Gaussian distribution, Gaussian noise on image, all on GPU. We've written this shit out and looked at it. I'm pretty happy with the results for the day. So, cool. I think we call it there. Thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 to 4 o'clock Pacific time. It is 3 o'clock Pacific time now. The research block didn't take as long as I thought it would today, so a little shorter. Some segments of this stream end up on the YouTube, and some do not. So today we spent maybe like half an hour, 40 minutes researching how you go from like an integer to a floating point number without losing precision. We implemented that here, but if you want to see like the exploration process of that, you know, you either had to be there to see it live, or if you subscribe on Patreon, join on YouTube, or subscribe on Twitch, you can see the VOD of that part in the appropriate spot. Twitch, you know, if you have a Twitch Prime, it's free. Maybe. So please consider supporting. You know, the stream will stop happening when I run out of money. And so this is like our way to get some, you know, give you guys something back if you choose to help the stream continue. Yeah, I think that's it. Thanks for watching. Happy with the progress today. YouTube, peace out, and Twitch, let's find someone to raid.